All right, in this example, we're going to go ahead and find the area bounded by two different polar curves. And again, we're going to use the graphs that we would have graphed in pre-cal or trig to really help out with the polar sketch and kind of see what we're looking at. Both of these are rigged or set up nicely so that I don't have to do anything. I can just use 0, pi over 2, pi, 3 pi over 2, and 2 pi, so those nice pole values. And so we're going to set up a table for both of these graphs, and then we'll sketch what the graphs look like. So we'll do two different colors. We'll do one of them in green, and then we'll do the other one in, I don't know, orange. So when we plug in 0, pi over 2, pi, 3 pi over 2, and 2 pi into green, we get 4, 2, 0, 2, 4. And then we'll do orange, and we'll plug in those same values. And you can verify that on your own, 0, 2, 4, 2, 0. And we'll go ahead and sketch that. Okay, so we'll sketch green first. Okay, so it's a rough sketch. It doesn't look great. I don't think my scale is the best, but it looks like there's too much room between 3 pi over 2 and 2 pi. But you get the idea, and then we'll put orange in. Notice that orange and green intersect at pi over 2 and 3 pi over 2. So we're going to use that when we do our graph here. So the highest we need to go is 4, so probably just each ring represents 1. So we'll go 1, 2, 3, 4. And we'll start by graphing some of, I think I started out with green. So at 0, we're going to be all the way out at 4. And then at pi over 2, we shrink down to 2. Now this thing has a horizontal tangent here, so we're going to have a certain amount of flatness here. And so we'll try to sketch that like so. So that's the first part there, and then we'll sketch the first portion of orange. So it does have some flatness there. It might be a little bit hard to do here, and it's going to go up to pi over 2. So maybe it looks something like that. If we want to be more accurate, we pick more values to plug in, but we're looking for a rough sketch. Okay, so we're not quite sure exactly where this region is that we're going to find yet, but it's going to be the region bounded between the two curves here. So let's continue graphing. So we'll graph some more of orange, and we're going to use the fact that they are symmetric. Okay, so they're going to be symmetric about pi. So we're symmetric about pi. Okay. So they'll look the same on the polar graph, just like they do on the little XY graph here. Let's see if we can get rid of that. All right, and we'll continue. Green is going to come on down like this. Okay, and so the area we're going to look at bounded between the two graphs, between both green and orange, or inside green and inside orange, is actually going to be this whole piece here and this whole piece here. However, because of the symmetry, we only really need to find the area of that little slice there that I have found, and then we can just multiply it by 4. We can actually do this piece here, the top piece, and this piece, and there would be 2 of them. Find that, and then if you weren't sure if it was really symmetric, then you could find this slice here and this slice here using green and the correct limits, and that'd work out just fine. Also, you'd come up with the same thing. So let's finish sketching orange. Okay, now we're going to go ahead and go from 0 to pi over 2, and that's going to be this region here, and that's going to be using the orange graph. So the orange graph is kind of bounding that area there, and then we're going to multiply that by 4. So our limits are going to be 0 to pi over 4. Okay. Now, if I wanted to do green, let's say I wanted to do this part separate, then that would be limits from pi over 2 to pi, and that would give me this region here. So it ends up working out that you can do it as one integral instead of two separate ones. Okay, so we have 4 parts, and the area formula has a 1/2. Limits are 0 to pi over 2, and orange was going to bound that particular region. So orange squared d theta. So we're going to have a 2 still outside here, and then we'll get a 4 squared there, or a 2 squared, which will be 4. So we'll get an 8 on the outside of our integral here. So 8, 0 to pi over 2, and then we'll FOIL, and we'll get 1 minus 2 cosine theta plus cosine squared theta d theta. We'll use our power reducing formula, so you'll have the 1 plus cosine of 2 theta over 2, and so the 1/2 will join the 1 to make a 3/2, so that's where that 3/2 is going to come from. So I think we did this in another video too, where we kind of skipped that step there. So 8, 0 to pi over 2, 3/2 minus cosine of theta plus cosine 2 theta over 2 d theta, and that'll be 8 3/2 theta minus 2 sine theta plus sine 2 theta over 4, and we're going to evaluate that from 0 to pi over 2. Okay, so when I plug in 0 and pi over 2, I'm going to get 0 and pi respectively, so that's not going to contribute anything. When we plug in 0 into this and this, that's not going to contribute anything. So essentially all we're going to be doing is plugging in the pi over 2 into these two terms, and that's the only thing that's really going to contribute anything. So we're going to have 8 and then 3/2 times pi over 2 minus 2 times sine of pi over 2 is just 1. So we'll distribute the 8, and we get 6 pi minus 16. Now, that other one I was suggesting is, well, what if we did that left side? You would be finding 2 of those sections times 1/2, and then we would go pi over 2 to pi, and then we would use green instead, and green was the 2 and 1 plus cosine of theta. We'll square that, d theta. And if you work that out, you get 3 pi minus 8, not 18, just 8, which is exactly half of that. So you could have done it that way also, but if we can do it as one integral, it works out a little bit nicer.